Okay, welcome to video class number 18. In this video, we are going to study about a transform. Okay, about a transform. You are very much familiar with this term transform after studying continuous time Fourier transform, then discrete time Fourier transform, that is DTFT, and in the case of continuous time signal, we also studied about Laplace transform. And this has more proximity or similarity with Laplace transform, which we have already studied in the case of a continuous time signal. Now, what is actually the need of Laplace transform? That I have already explained in the previous video. That is, Laplace transform is meant for those signals which does not have a Fourier transform. That is, a Fourier transform will not exist for every signal. There is a condition for a signal to have Fourier transform, and the condition is the signal has to be integrable, or in other words, it has to converge to a particular value. So what is the meaning of converging? That is, say if you have a signal x of t, when you integrate that x of t from minus infinity to plus infinity, that has to give a finite value. And if it provides a finite value, that is integrable. But there are some signals like u of t, r of t, ramp signal. All these are a periodic signal. We may think that they have Fourier transform, but that fails on this condition, fail to achieve this condition. Therefore, those signals, those class of signals, will not be having a frequency domain representation in the form of DTFT. In such cases, we require transform called as a Laplace transform, and we have already studied in this. I'm just giving you a recap of that. So we have defined this as Laplace transform as x of s, and it is given as minus infinity to plus infinity x of t multiplied by e raised to minus st dt. You are integrating this product x of t into e raised to minus st from minus infinity to plus infinity. So you will be getting a function in S domain, and we know that S is defined as sigma plus j omega. So we also understood that S is a complex plane with real axis and an imaginary axis, but that's a linear plane. Okay, now after knowing all these things, you are very much familiar with the transform. So we also studied under DTFT, there are some signals like u of n, r of n, and those signals will not converge. So in a discrete time signal, what the convergence refer to is, so instead of integrating, you can submit an x of n, as n varies from minus infinity to plus infinity, should also provide a finite value. And for signals like r of n and u of n, they will not be converging when you put this into this equation. That means that won't be having a finite value. So such signals will not possess DTFT of its own. So therefore, in order to have the frequency representation of this type of discrete time signal, we need a transform, and that transform is called as a Z transform. Okay, now so let me go into the definition of mathematical representation of x of z. So as you all know, this is a signal, this is a transformation of a signal. That means similar to DTFT, this can also be converted into, similar to Laplace transform as well, a signal x of n can be converted to a function of z. So call this as x of z. So we will call this tool or this process as called as a Z transform. And if you have an x of z, from the given x of z, you can get back your x of n, and we call that as the inverse Z transform. So for this, to convert a signal x of n to x of z and vice versa, you need an expression, and we can have this the expression of x of z as x of z is equal to, so let us compare with this of x of s. Now what is this x of s? Now how will you get the x of s? This x of t is multiplied by e raised to minus st. So you take your x of n, multiply that by, what is e raised to minus st? E raised to minus st is called as a Laplace kernel, or you can think of this as a window. E raised to minus st is a window through which you look at x of t. So you will be seeing x of s. That means you are no longer going to see x of t as such, but in a different figure that we call as x of s, or rather in a complex way. So similarly, here also, instead of this e raised to minus st, you have a exponential discrete time signal, say z raised to minus n. So z raised to minus n is said to be the z transform kernel through which you look x of n. Now x of n is no longer an x of n, this will be your x of z. Now what else? Now this product is integrated from minus infinity to plus infinity with respect to time. Since it is discrete, you cannot work with integration, that is summation. You need to employ summation as n varies from minus infinity to plus infinity. So that is your x of z. Now similarly, now we know that what is this z? We have already defined s to be sigma plus j omega. That means this is a complex linear plane. Similarly, z is defined as r e raised to j omega, and there lies the difference between the s plane and z plane. Now this represent r e raised to j omega is nothing but r cos omega plus j sin omega, or in other words, this represents a circle, right? So this is also a complex plane, but this is a circular plane with r being the radius of the circle, and this is your angular omega, right? So what is this r into cos omega plus j sin omega? What is the magnitude of cos omega plus j sin omega? It is root of cos square omega plus sin square omega, which always equal to 1, but that omega varies. That is, as the frequency varies, this traces a circular path. Okay, that means this is a circular plane. So z is a circular plane, but it is also a complex plane. So this is a very important definition of what z is. Now if you are given with x of z, how will you find of x of n? So now the x of n is called as the inverse z transform, IZT, or inverse z transform. Now how will you get that? X of n is given by 1. So here, since we know that this is x of z is a complex signal, so this must be multiplied by z raised to n minus 1, and this is again a complex quantity, and you need to integrate, and that too a closed contour integration. That means this is divided by 1 by 2 pi j into dz. So what is the meaning of this contour integration? You are integrating not from one point to another. You are integrating on a closed path. That's the difference between the normal integration and this contour integration. You are integrating over a closed path or a contour, right? So that's a complex integration. So this is your x of n. So x of n seems to be very complex, or seems to be very tedious to find out, but we will be seeing various methods to find out the inverse of z transform. Now let's try to do some problems using the basic expression of z transform. So I am rewriting that expression once again, that is n is equal to minus infinity to plus infinity x of n z raised to minus n. Now we have to do some problems. So before that, I am again classifying this x of n to be of two groups, two categories. One is a finite duration sequence, and infinite duration sequence. Okay, so in your x of n can be of finite duration sequence. What's the meaning of finite duration sequence? Say for example 1 to 1. That means this particular signal is having only 3 samples, that is x of 0, x of 1 and x of 2. Now for another example is 1 2 2 1, and what's the difference? It has got 4 samples, but it is having it is also having a finite duration after the third sample, that is 0th sample, first sample, second sample, third sample. After the third sample onwards, that signal is going to be 0 throughout. While in the case of an infinite signal, we know what is u of n, that is a signal of this type. So this is equal to 1, and it goes on like that. So you have, even though the amplitude is constant, but it has got samples from 0 to infinity. So that means such type of signals are called as infinite duration sequence. Now we are going to find out your x of z under two categories. So we are going to deal this x of z, or finding out x of z under two categories, that is z transform of finite duration sequence and z transform of infinite duration sequence. Okay, now let's start with z transform of finite duration sequence. Okay, now for that I'll be just find the z transform of the following sequences. Number 1, x of n equals given as 1 2 2 1. Okay, so this is 1. So this one is a 0th sample. Now what is your x of z? X of z is equal to sigma n is equal to, you don't have to use from minus infinity because the sample starts from 0. If there is no arrow, you can assume the first sample to be the 0th sample. So n varies from 0 to 0, 1, 2, 3. Yeah, only 4 samples. So n only varies from 0 to 3. X of n is z raised to minus n. So just try to expand as such. X of 0 into z raised to minus 0 plus x of 1 into z raised to minus 1 plus x of 2 into z raised to minus 2 plus x of 3 into z raised to minus 3. Okay, now let us substitute from the sequence. What is x of 0? It is equal to 1. So 1 into z raised to 0 is 1, right? Now 2 plus x of 1 is 2. 2 into z raised to minus 1. Then next one is x of 2, which is again 2 plus 2 into z raised to minus 2, and x of 3 is 1 again. So this is 1 into z raised to minus 3. So that this becomes 1 plus 2 by z plus 2 by z square plus 1 by z cube. Okay, now if you are simply writing like this x of z, then the examiners can put this, you may lose some credits. Why? It is a very must to speak about the existence of this x of z. We know that x of z is that means this x of z can be in this plane or outside this plane. Okay, whatever it is. So it can be inside a circle or it can be outside a circle. Because it's a circle, so you need to define this from where all this x of z exists. Okay, now we know that x of z exists. What happens at z is equal to 0? When z is equal to 0, all these terms becomes infinity. That means it is not defined. So you will have to write that this exists for all z except z is equal to 0. Okay, this is a very important statement that you need to write about the existence of z, and the existence of z transform must be definitely specified when you deal with infinite duration. It is more important when you deal with infinite duration sequence than this. Anyway, it is a good practice always to specify about the existence of z. So you can say that this x of z has got, or this particular signal has got an z transform like this, but it exists for all z but except at z is equal to 0. That means that is at the origin. Except at the origin, this particular signal will be having the z transform anywhere on the z plane. Okay, now let's move on to the second problem, that is x of n is equal to 1 2 2 1, where this 1 is the 0th sample. Okay, now in this case we know that this, so if you are to draw this figure, this will look like this. So this will be 1, then you have 2, then another 2, then you have a 1. So this will be 0, minus 1, minus 2, minus 3. Now if this is the case, what will be your x of z? Now x of z, it actually starts from n equals minus 3. Minus 3 to how much? Minus 3 to 0, right? X of n, rest of all are 0. So this is equal to z raised to minus n. Now what you will, when you expand this, expand from x of minus 3. So when you put n is equal to minus 3, this becomes minus of minus 3. So z cube plus x of 2, x of minus 2 into z square plus x of minus 1 into z plus x of 0 into z raised to 0. So in other words, you can say, when you substitute this, x of minus 3, which is equal to this 1. So this is 1 into z raised to 3. Z raised. So this is 1 into z cube. Second one is x of minus 2 is 2. So this is 2 into z square. X of minus 1 is again 2. That is 2 into z plus 1 into z raised to 0. Or you can write like this: 1 plus 2z plus 2z square plus z cube. Okay, so what can you say about the existence of Z transform? Here also you need to specify about the existence of Z transform. Here you can say that all Z except there is a point in this is a Z plane varies from, so the radius can vary from 0 to infinity. So except at Z is equal to infinity. So this x of Z becomes indefinite, or it is not a definite value only at Z is equal to infinity, except at Z is equal to infinity. So that's what you need to refer. Now you can have another signal like this, the same signal. So not that these are all, the samples are all the same, but it varies in the time frame. That is, here the 0th sample starts from here. Now here you have only the negative samples, including then 0. Then say another example, 1 2 2 1, same samples, same question, but the arrow is just underneath this. So when you write this x of z, you can write this as, so this is, if arrow is under this, you can say that this is the 0th sample, this is the first sample, minus 1th and minus 2th sample. So that means you can have this as minus 2 to 1 x of n z raised to minus n. Now just expand, I'm not going to write again this. When you expand and substitute from this samples, you will get x of minus 2. What is x of minus 2? Which is 1. 1 into z raised to minus n. Minus n of minus 2 is z square. Second term will be 2 into z raised to 1. The third term will be, again you have 2 into z raised to 0 plus 1 into z raised to minus 1. So this can be written as z square plus 2z plus 2 plus 1 by z. So what can you say about the z transform of this? All z except, you need to discard 2 points. That is, what happens at z is equal to 0? Z is equal to 0, this becomes infinity. Now what happens z is equal to infinity? This becomes infinity. So x of z will become indefinite at 2 points. That is, at z is equal to 0 and z is equal to infinity. So when you talk about the existence of this transform, if you are not writing any condition, that means it exists for all z. That's wrong. So for these three cases, we have found out it is not, x of z exists for all z except at some points in the case of a finite duration sequence. Okay, now let's look at the z transforms of the problems we have just done. So the first case was a simple x of n, where you can see that the first sample is, so look at this, the first sample is the 0th sample, first sample, second sample and the third sample. You found out the z transform of this, and when we found out the existence of z transform as all z plane except at the origin, that is at z is equal to 0. Now when you come to the second part, where you have the 0th and the negative time, in that case you will be having an z transform like this, but the z transform exists to all z except at z is equal to infinity. And what about this? this is actually having a positive part as well as a negative part. So in that case, all z except at z is equal to infinity and 0. So from this you can generalize an finite duration sequence as this can be thought as a causal sequence where it is defined only for the positive time. Okay, this can be considered as a causal sequence. So it will be all z except at z is equal to 0. Now in this case, this can be called as a non-causal or an anti-causal signal where you have only the negative values. I mean, if you are ignoring the 0, anyway, we can see that all z except at z is equal to infinity. Now if it is a double-sided signal, then you need to exclude 2 points, that is z is equal to infinity and z is equal to 0. This is general, and this is applicable for, this column is applicable for any general causal signal, non-causal signal and DS signal. Whatever you may do, whatever causal signal you may try, you can see that that Z transform exists to all Z except at Z is equal to 0, and likewise these two cases. Okay. Now next is to find out the Z transform of infinite duration sequence. So for that, and let's do some problems, and similar to this treatment, so where we have generalized this finite sequence, we are also going to generalize this infinite duration sequence by doing some examples, and from those examples we'll draw out some conclusions. Okay, find the Z transform of the following infinite duration sequence. So number 1, U of n. You know what is U of n. I'm just drawing it for you again. It is U of n. This is 1, 1, and it goes on up to infinity. So this is your U of n. Sample starts from 0, 1, 2, 3, etc. up to infinity. Now what is your expression then? X of z, you don't have to use n is equal to minus infinity because n varies from only 0. So it starts from n is equal to 0 to infinity. X of n is z raised to minus n. So what is this? Now this x of n will be always equal to 1, whatever may be the sample. So n is equal to 0. So the first sample will be 1. Plus second one will be z raised to minus 1, 1 into z raised to minus 1 plus 1 into z raised to minus 2 minus 3 and so on, right? It goes on. So as we have studied already, this is actually a geometric series. Now this geometric series is going to infinity. So now the question is, if this x of z does not have any meaning because it goes on to infinity. So this series, if it wants to have any meaning, this series has to converge, right? Now we know that from our mathematical knowledge that, see, if you have a geometric series with a common ratio r, and if this r is less than 1, you can say that this particular geometric series will converge to a sum as 1 by 1 minus r. So this is a thing which we have already studied in our lower classes. Okay, that is, if you have a geometric series of the form 1 plus r plus, so of the form 1 plus r square plus etc., what is the common ratio? Common ratio between each term will be r. Now if this r is less than 1, then this particular series converges to 1 by 1 minus r, meaning that it can have the total sum will be arriving at a sum or converging to a sum given by 1 minus r. Now if suppose r is greater than 1, what happens is it won't converge, it will go to infinity. The sum will be equal to infinity. So that's the meaning of converging. Now what about the common ratio in this case? Now this x of, if you write x of z like this, it doesn't have any meaning at all because it goes on to infinity. Of course, when we studied finite duration, this has got meaning because this is not going up to infinity. This has got only some finite terms, and we know that this only the existence of z transform you need to specify. Yes, all z except at z is equal to 0. But in this case, it is going on to infinity. Now, if it requires a meaning of it, or if it requires a shape, then you need to find out some way by which this geometric series need to converge to a value, and we found out this. From this we can find out this common ratio as z raised to minus 1. Now if you can assume so this particular signal or this particular x of z will be having a meaning only if it converges. Now what is the condition for converging? That is, the common ratio has to be less than 1. So if you impose a condition, that is modulus z raised to minus 1 is less than minus 1, you can straight away write this using this equation. You can straight away write this converges to a value 1 by 1 minus z raised to minus 1, or this will be 1 by 1 minus 1 by z, or this is equal to z by z minus 1. Okay, fine. So this is actually your x of z. Now what about the condition? If you are writing without this, if you are just simply finding out, the answer is absolutely wrong. What does this mean? This means that you have this u of n has an z transform everywhere in the z plane. That's not the right fact. Let's see where it is found out, where the z transform exists for this u of n. Now you have already found out this mod z is greater than minus 1 less than 1. Now just I am doing it just to make you understand the meaning of this. Now what is this? Mod z greater than minus 1 is less than 1 means 1 by z is less than 1, or z is greater than modulus z is greater than 1. Now what is z? From our previous discussion, we have already defined z to be, what is z? Z is equal to r e raised to j omega, right? Okay, now you can just straight away put that as modulus r e raised to j omega is greater than 1. Now what is the modulus of e raised to j omega? E raised to j omega, we know that it is cos omega plus j sin omega. The modulus is greater than, modulus is 1. So that means it is r greater than 1. What does that suggest? R refers to the z plane radius. So it's a circular plane, as I already mentioned. So this must be a region. So this must represent a region, a outside portion of a unit circle that you draw in a complex plane, in an z plane. So if you can draw a unit circle, and this x of z, or the x of z of u of n, or exist only in the region where z is greater than 1, or outside the unit circle drawn in an z plane. That means you don't have this u of n doesn't have an z transform inside the circle. Okay, so you can consider this as the region. So it can also be called as a region where this series converge. Therefore this mod z is greater than 1 is called as ROC, region of convergence, or it is the region where this infinite geometric series converges. Hence that region is called as ROC. Okay, in the later examples you will understand what is the importance of ROC. ROC is so important. If ROC is not specified along with this Z transform, you are not going to get any credits. Okay, so ROC is, so you will be asking why ROC is so important. I will be explaining that after doing some more examples. We will have a comparison of that, and by that I will be explaining the immense importance of ROC. Okay, now let's move on to the second problem. Second infinite sequence, that is, say x of n is given as minus u of minus n minus 1. So let's first of all see what is this u. You already know that. I'm simply drawing it for u. This is u of n, right? This is u of n. Now what is u of n minus 1? We know that u of n minus 1 is this thing. This is 0, 1, 2, 1, 1, 1, 1 and so on. 0. So this is 0, 1, 2, 3, etc. 0, 1, 2, 3, etc. Now what about this is u of n minus 1. Now what will be minus of u of minus n minus 1? So this is, next is, when you draw u of minus n minus, that is minus n minus 1, means you are placing a mirror over here. Looking through that mirror, you will be getting a shape of that mirror. So that will look like this, right? So right now we want minus of this. So what will this signal look like? This signal will be like this, right? So this is minus 1, minus 2, minus 3 and so on. So okay, all these values are minus 1 each. Here you have 0. Okay, so this is how it is. Okay, now I'm going to find out the Z transform of the signal. X of Z is equal to sigma n is equal to minus infinity to plus infinity x of n z raised to minus n. And in this case, since it is since the signal varies only from -1 to -1, so you can write like this: sigma n is equal to, so you can take this minus outside. Okay, you are putting, so this u of n will be always having a the value will be always equal to -1. So this can be written as n is equal to minus infinity to -1. So this is z raised to minus n. So when you take this is minus of expanding this, you will get this as z raised to 1, right? Minus of minus 1 plus z square plus z cube plus etc., right? Now this is again a series, a infinite series. Now what happens if I take z outside? So when I take z outside, you can see that this will be 1 plus z square plus etc., right? Now this is again a geometric series with a common ratio z. Now if you can assume this mod z is less than 1, you can write this, or this signal or this geometric series converges to a value 1 by 1 minus z, right? Or you can give, by this minus, taking a negative sign here, this negative cancel, so that this becomes z by z minus 1, or mod z is less than 1. What is the meaning of mod z less than 1? Mod z less than 1 is r e raised to j omega is less than 1. We know that e raised to j omega is 1 magnitude, so r is less than 1. What is the meaning of that? R less than 1 means it is again an z plane. You have a unit circle, but it is the interior of the z plane, not the outside. So what you say about minus u of minus n minus 1, or rather this signal will be having an x of z by z minus 1, not the outside the circle region, but only in the region inside this unit circle. So therefore this is called as the ROC of this signal. So I again repeat, ROC is very important when you find out the z transform. It has to be specified. Okay, now let's move on to the another problem. That's the third problem. Find the z transform of x of n given by a raised to n into u of n minus b raised to n into u of minus n minus 1. That means it is a combination of two signals. Basically it is actually the two problems we have done almost individually. So it is a combination of those previous two examples. Now in this case, what you can do is you can find out, when you find out x of z, it's nothing but it is a sum of the individual z transform. That is actually the linearity property which we have already studied in various transforms. So you are very much familiar about that linearity property. So this can be written as, say, this can be written as plus of minus. So this is plus of z transform of minus b raised to n into u of minus n minus 1. Okay, now we know that. Now how to find out the z transform of a raised to n into u of n? A raised to n into u of n. Now what will be this? So sigma n is equal to, since it is multiplied by u of n should vary from 0 to infinity, a raised to n into u of n into z raised to minus n. Now u of n can be written as 1. Okay, for every positive values of n, this will be equal to 1. So that means this is n is equal to a raised to n into z raised to minus n. Now upon expanding, you will get this as, when you put n is equal to 0, the first term becomes 1. Second term, that is n is equal to 1, you will be having a into z raised to minus 1 plus a square into z raised to minus 2 plus a cube into z raised to minus 3, and so on. So this is actually a geometric series of the form 1 plus r square, etc. Now if you can impose a condition modulus r is less than 1, you can straight away write this as 1 by 1 minus r. That means what is the common ratio? Common ratio is a into z raised to minus 1. Now if you can impose this condition, that is a z raised to minus 1 is less than 1, or a by z is less than 1, right? Now bringing this z here, you can write this as mod z is greater than a. Now if you can impose this condition, you can write this infinitely going series as a converging series, as or it will converge to a value 1 by 1 minus the common ratio a into z raised to minus 1, or this is 1 by a by z, or bringing this z and okay, so you will be getting this as z by z minus a. Now what is the meaning of this? The meaning of this is r e raised to j omega is greater than a, or when you take the magnitude of e raised to j omega, it is 1, so it is r e raised to r greater than a. So what's the meaning of this? This is actually, this represents that is this particular series converges only in a particular region where mod z is greater than a. That means if you can draw a circle with radius a, there will be a region outside the exterior portion of the circle. We'll call this as the exterior of the circle with radius equal to a. So in this, so what is the specialty of this region? This is the region where this particular signal has its transform, or conversely you can say that this particular signal will not be having an z transform inside the circle. Okay, so this is a very important thing. I again repeat that ROC is a very important aspect when you find out the z transform. Z transform is an absolutely meaningless if the ROC is not mentioned. So here in this case, this is valid only for a region where mod z is greater than a. That means only for the exterior region of a circle with radius a. Now similarly, you can find out the z transform of minus b raised to n into u of minus n minus 1, right? Now what about this? This is sigma n is equal to, it starts from minus infinity, right? Because it is u of minus n minus 1. We have already seen in the previous example. Okay, I'll show you. So look at this. So here it is. So this is u of minus n minus 1. That means it starts from minus 1 to up to infinity. So if that is the case, you can write this as minus infinity to minus 1, and you can take this minus outside. Okay, there is a minus here, so you can take this minus outside. B raised to n into 1 into z raised to minus n. Now putting minus 1 onwards, now as n varies from minus onwards, you can write minus of what? B raised to minus 1 z, right? When you put minus 1, it becomes minus of minus, then b minus 2 z square, b minus 3 z cube. Now similarly, so here you can take what? You can take this b inverse or b raised to minus 1 z outside, so that this becomes b inverse z plus b inverse minus 2 z square, etc., right? So that means this is again a geometric series, and if you can assume this b inverse z, this is your common ratio. If this common ratio is less than 1, you can write this as minus b inverse z into 1 by 1 minus b inverse z. Okay, now here again, so that is equal to, okay, that is equal to I'll rewrite again b, so okay, that is z by b, that is this b inverse z can be written as z by b into 1 divided by 1 minus z by b, right? Okay, z by b, right? So this will be minus z by b into 1 divided by b minus z, okay, into b. This b and b cancels. Okay, so now taking this minus out into this, so you can write this as z by z minus b. Now what about the ROC? ROC is, here we have assumed that the common ratio b inverse z is less than 1, that is z by b is less than 1, or z is less than b. So what do you infer from this? The ROC is, okay, so this is in contrast to this. So this is going to be a circle with radius b. It's not a radius b, but it is the interior portion. Look at this. So in this case, the ROC exists for this outside the circle with the radius a, while in this case the ROC exists inside the circle with the radius b. Okay, now this is it, z by z minus b. Now, but you are asked to find out the z transform of this combined signal. That means this x of z is nothing but the z transform of this plus z transform of this. We have found out this to be z by z minus a plus z by z minus b, right? Z by z minus b. Now the question is, can you write like this? Now there must be a condition. See, if this two when you sum up this, if it there must be a ROC to this. What is the ROC of a combined signal? Obviously there must be an intersection region. Now let us combine this ROC. Let us combine this ROC together. One is mod z is greater than a, another one is mod z is less than b. Now how to combine this? Say one signal corresponds to a region greater than a particular value, one signal corresponds to a region less than b. So this will happen only if there is a condition called b is greater than a. That means I will just draw it for you. That is the say I am going to draw a small circle. That means if b is less than a, then that means a is smaller than b, and I am drawing another circle with the radius b, right? So this is radius b. Now just read out. First one is z by z minus a is having a modulus z greater than, that is this region greater than a, and this is less than b. So that means the region is in between the radius a and b. So that means the combined ROC will be a less than b, right? So this is your ROC. So what is this type? This is actually a ring, annular ring shape. The annular ring shape is the shape of this ROC, right? So this individually, this particular signal is outside a circle, this one is inside a circle, but when you combine this becomes a strip, a circular strip, and we call that circular strip as annular ring. So what happens if a is greater than b? A is greater than b means a is greater than b. I will be drawing that as well. What if a is greater than b? Suppose this is b and this is a, that means in this case a is greater than b. Now what is mod z greater than a? Mod z greater than a is the region outside this. Mod z less than b, this is inside. So in nowhere the signal gets intersect. That means as long as b is less than a, this particular signal will not be having any ROC. So imposing a condition like this, b is greater than a, only you can have an z transform, and that too not in the whole z plane. That will be only in between the region a and b. So that is called as an annular ring. Okay, now I'm going to have a recap of what we have studied under the z transform of infinite sequence. So first example we did was u of n, and we found out the answer to be z by z minus 1, and the ROC we found out to be mod z greater than 1. Okay, now instead of this, if it would have been a raised to n, we have also done a raised to n into u of n. Okay, so that will be z by z minus a, you have proved, and at that time this modulus z will be greater than a. Okay, now the second example was u of minus n minus 1. So this was z by z minus 1, while mod z is less than 1. And if it would have been say b raised to n into u of minus n minus 1, we have found out that z by z minus a, while mod z is less than b, right? Now combining these two signals, we have done the third problem as combining these two, that is a raised to n into u of n plus minus b raised to n into u of minus n minus 1. So we found out that to be z by where b is greater than a. This is the condition. Okay, so if that is the condition, we have proved that z by z minus a plus z by z minus b. So for that case, what is the ROC we have found out? So this modulus z lies in between a and b. Okay, so this we call as this is generally we will call as the exterior of a circle. This is called as the interior of a circle, or this one we call as a circular strip, or this is a circular strip, or we call that circular as a annular ring. Okay, now what I'm just going to generalize this. What category of signal this is? This is a causal sequence. Why this is causal? Because it is u of n. Here also it is multiplied by u of n. That means that's going to be a signal which is defined only in the positive half. So that is a causal signal. So for whatever causal signal, that will be exterior to a particular circle with radius. Say it need not be always 1. It can be greater than a or greater than b, or whatever it is. So anyway, it will be an exterior region of a circle. Well, what about this type signal? This is an anti-causal signal or a purely non-causal signal. Now, if it is what is a non-causal signal? Non-causal signal is a signal which is defined only in the negative half of the. Okay, now we have seen that. Now, for such signals, always the ROC will be an interior portion of a circle. Okay, so that circle radius is determined by the parameters or the constants. Okay, anyway, what if it is an anti-causal signal, then the region of convergence will be interior to the circle. Now what about this case? When it is a combination of, this can be called as a double-sided signal. Okay, now in some textbook this may be called as a right half sequence, especially that terminology is used in the case of a finite sequence. Causal sequence may be called as a right half signal, anti-causal may be called as a left half signal. This is called as a double-sided signal. That means the explanation is simple, that is the combination of a causal sequence and an anti-causal signal. Now if it is an anti-causal and a causal signal, then that will be between a region. So that always whatever double-sided signal you are going to find, you are going to see that its ROC is a annular ring. Now let me explain why ROC, as I mentioned to you earlier. Later I will explain that what is the immense importance of ROC. Look at these two cases. We know that these u of n and minus u of n minus n minus 1 are entirely two different signals, right? Okay, no way that it matches. So that is, these two are two different signals. Look at its Z transform. Both the Z transform are the same, and they only differ in their ROCs, right? They only differ in their ROCs. One is exterior to the circle, another one is the interior to the circle. So what you can infer from this? You can infer from this as a signal x of n, two different signals, two or more signals can have the same Z transform. Okay, now if it has got two same Z transform, see, what will you do to identify this? Suppose if you are asked a question to find out the inverse. Now that inverse can be u of n as well as minus u of minus n minus 1. So which one will you select? So that's a problem. So you definitely require the knowledge of ROC. So if the ROC is mod z greater than 1, then you can say that this represents u of n. If this is the ROC, then you must you can represent this as, or you can find out the inverse as minus u of minus n minus 1. So from this you need to have an inference or a general statement that two or more signals can have the same Z transform. But now the question is, how will you differentiate that if it has got a 2Z transform? Yes, you can differentiate by the ROC, but they differ in their ROCs. Okay.